Alright, and this follows from this nice little thing that is called Abel's formula. Alright, so suppose that we have a second order homogeneous ordinary differential equation. And suppose that y1 and y2 are solutions of the same differential equation. And so then, according to Abel's formula, the Wronskian is given by the following equation. So it is some constant times e to the minus antiderivative of p of t dt. So in other words, notice that it is very, very similar to the integrating factor from the second week. So like, let me write, like mu of t from week 2. The constant c depends on the pair, so it is possible that y1 and y2 are proportional to each other, so then of course the Wronskian should be 0, so then c should be 0. But not on t, right? So c is a constant. Then notice that it means that the Wronskian can never be 0. So I mean, since the exponential function of anything is always positive, it means that the Wronskian is, if c is positive, then the Wronskian is positive for all values of t. If c is 0, then the Wronskian is 0 for all values of t. And then the two functions are linearly dependent. Or if c is negative, then the Wronskian is negative for all values of t. Okay, so let us prove this formula. Again, it's very, very nice. So since both y1 and y2 satisfy the differential equation, so we can write it down. But then what we are going to do, we are going to multiply the first equation by, so let me write it, by minus y2, and we are going to multiply the second equation by y1. And the reason is because if we do this, then here we are going to get minus y1, y2. Here we are going to get y1, y2, so they will cancel each other. And here we are going to get the Wronskian exactly, right? So if we do these multiplications and add the two equations, what we obtain is this. So the whatever was at q of t just cancelled out, and whatever was at p of t, we get the Wronskian. But also notice that this thing is our Wronskian, while this thing is actually just the derivative of the Wronskian. Now you can verify it. Well, let me do it, right? So if the Wronskian is y1, y2 prime minus y1 prime, y2, then the derivative of the Wronskian is going to be this whole thing derivative, y1, y2 prime minus y1 prime, y2. Now everything prime. Now the derivative of the first term by the product rule is going to be y1 prime, y2 prime plus y1, y2 double prime. The derivative of the second term by the product rule is going to be minus y1 double prime, y2 minus y1 prime, y2 prime. And now y1 prime, y2 prime minus y1 prime, y2 prime cancels out, and the answer is y1, y2 double prime minus y1 double prime, y2, which is exactly this. So in other words, the Wronskian satisfies a differential equation itself. W y prime plus p of t times w of t. And I hope you recognize it. It is a first order linear differential equation with the unknown function w of t. And then you can multiply it by the integrating factor, and the integrating factor here is exactly e to the antiderivative p of t dt, and so on. I think you can do it yourself, so that you see that the solution is exactly as it is claimed in Abel's formula. So, and again, let me emphasize again that once we specify y1 and y2, then the Wronskian could be different. So this C depends on specifying y1 and y2. The reason is because this is a differential equation, of course, but we don't have the initial condition. Right, so which means it has many solutions, but these different solutions, they differ from each other by changing the constant. And this changing the constant, it kind of corresponds to changing the original pair y1, yt. Alright, so we have proved Abel's formula. And here is a little example. Right, so speaking of our original differential, well, one of our initial examples, so we found two solutions, and then we can find the Wronskian. And in this case, in Abel's formula, Abel's formula tells us that the Wronskian should be some constant c times e to the power, my p of t is 5, so it should be minus the antiderivative of 5 dt, so which is c e to the minus 5t. Right, so in this case, this c happened to be minus 11. But since it is non-zero, we conclude that y1 of t and y2 of t are they are linearly independent.